Welcome back, and use your knowledge from last week's exponents review to help you simplify these 6 warm-up questions. Number 1, we have 2 to the 3rd times 2 to the 4th. Remember, you should be adding your exponents, so it should be 2 to the 7th. Question number 2, we have x to the 5th times x squared all over x cubed. So for this particular problem, it's going to be x to the 7th over x cubed. So where do you have more x's, top or bottom? You have more x's on the top by 4. Okay, number 3, you should have, it is going to be 2b to the 5th times 2b to the 5th times 2b to the 5th. So 2 times 2 times 2 is 8, and we have 15 b's. Number 4, our bases are the same. Oh, let's put this back down. Why? There we go. All right, on number 4, we have the bases are the same, so we're going to add the exponents. This one's kind of a little weird. It's just going to be 3 to the x plus 5 power, and I am going to put it in parentheses to make sure that we know that plus 5 is up in the exponent spot. Okay, number 5, we're going to combine like terms. First, y to the 4x times y to the x. That will simplify to y to the 5x because we're going to add them. 4x plus 1x is 5x over y to the 2x. So where do we have more y's, top or bottom? Well, we have more y's on the top by how many? Well, 5x minus 2x is 3x. And then number 6, we have 3ax times 3ax. So, whoa, let's try that again. 3a to the x times 3a to the x. Okay, so 3 times 3 is 9. A to the x times a to the x is going to be a to the 2x because we're going to add these exponents. X plus x is 2x. On our next screen in our notes, our essential questions today are going to be, what is the difference between exponential growth and exponential decay? What are the key characteristics of exponential growth and decay graphs? And how can I use exponential growth in real life? So our core concept is going to be the exponential growth function. There's a couple of things you need to know about the exponential growth function. We write this function as f of x equals b to the x, where b is the base, x is the exponent, and that's why it's called an exponential function, because your variable is now up at the exponent. The domain is going to be all real numbers. And depending on who your teacher was last semester, you could have written all real numbers like that, or you could have written all real numbers in words, or you could have written all real numbers in symbols from -infinity to infinity. And the range, bringing it right here, is going to be y is greater than 0. Y cannot equal 0, and y cannot be negative. So this is going to be important to know. One also key characteristic from this graph is that this graph has an asymptote. So an asymptote is a line that the function gets very, very close to, but usually will never cross. And I say usually because there are some exceptions later on in math that we'll talk about. But for exponential functions, the graph will never ever cross this exponential function, this asymptote. And the asymptote in this case is going to be y equals 0. And there is a connection between the asymptote and the range. Those two numbers will always need to be the same. Okay, we have here another exponential function. And in this case, we have f of x is equal to b to the x, but this time, b is going to be between 0 and 1. So our base is going to be a fraction less than 1, which ends up flipping our graph around, reflecting it over the y-axis. But all the other information is still the same. The domain is still going to be all real numbers. The range is still going to be y is greater than 0. And the asymptote is still going to be, in this case, y equals 0 because we have not shifted the graph. There are 3 points that I want you to graph with every exponential function. And those 3 points are going to be 1, comma b, 0, comma 1, and negative 1, comma 1 over b. And we'll talk about this when we go to graph our exponential functions. When you have, say, y equals 2 to the x. If I put in 1 there, 2 to the 1 is going to be 2. So the 3 ordered pairs I want are going to be 1, 2, 0, 1. Because if I put a 0 in here for x, 2 to the 0 will always be 1. And if I put in a negative 1, 2 to the negative 1. So let's see, 2 to the negative 1, remember from last week, our exponent is going to, negative exponent is going to cause a fraction. So that will be 1/2. All right, so tell whether each function represents exponential growth or exponential k. It all has to do with the bases. If the base is greater than, and I'm going to put this absolute value bar here, but if the base is greater than 1, it's going to be growth. And I want these absolute value bars here just because we're talking about positive bases. We're not talking about negatives at all. Bases cannot be negative. Those negatives are reflections. And if the base is going to be between 0 and 1, it is going to be decay because it's getting smaller and smaller and smaller. So let's take a look. Our first problem here, y equals 2 to the x. Our base is 2. Because 2 is greater than 1, it is going to be growth. And if we look at option B, we have a 1/2 here. That 1/2 is between 0 and 1. So because our base is 1/2, this is going to be decay. Okay, our next slide, tell whether the function represents exponential growth or exponential decay. Please pause the video, try these on your own, and come back and check. Okay, number 1, the base is 4, so that is growth. Number 2, the base is 2/3, so that is going to be decay because it's smaller than 1. Number 3, your base is 0.25. That's smaller than 1, so this is going to be decay. And on number 4, your base in this case is 1.5, so that's bigger than 1. That's going to be growth. I hope you got those right. Slide number 7. What would be a general formula for exponential growth and decay? And what determines if it's growth or decay? Let's actually answer that last question first because that will help us create general formulas. If it's growth, we said the base has to be bigger than 1. And let me write here that the base is bigger than 1. And if it's decay, the base is less than 1. So each of these numbers go around, each of these bases are deciding whether or not if it's greater than 1 or less than 1. So a general formula for exponential growth could be something that looks like this. F of x equals 1 plus the rate of growth to the x power. Because no matter what r is going to be, as long as r is positive, we are going to have a number bigger than 1. And for decay, because we want a number smaller than 1, we want 1 minus r, the rate of decay, to the x power. So question number 8. The value of a car, y, in thousands of dollars can be approximated by the model 25 times 0.85 to the t power, where t is the number of years since the car was new. And we are going to assume here that you did not pay $25 for the car, but you probably paid $25,000 for the car. So part A says, tell whether the model represents exponential growth or decay. So what's our base for this problem? Our base is 0.85. That's less than 1. So this has to be decay. And it says identify the annual percent increase or decrease in the value of the car. Well, because it's less than 1, we know that it has to be a decrease. So 1 plus r has to equal 0.85. So if we want to solve for r, we're just going to subtract 1. And if you need to use your calculators for this, this is okay. 0.85 minus 1.00 is going to give us negative 0.15. So our decreasing rate is 15%. And I know it's decreasing because it's negative. To estimate the value of when the value of the car will be $8,000. So for this problem, we are going to go to Desmos.com at this point in time. And I first want to put in the value of the car option. So the value of the car was 25, and then parentheses, 0.85 to the x power. So I need to do shift 6 here. Where's my shift button? There we go, shift. And in that case will be my exponent spot, that little caret, to the x power. And we're going to say equals y. So equals y. So there's our function. So 25 times 0.8 to the x power equals y. So how come our graph isn't showing up? Well, remember, our graph is really starting at 25,000. So I'm going to zoom out here a little bit. And there's our exponential function. And now it's asking us for when is this going to be 8,000. I don't really want to put 8,000 in here. I want to put in 8. Because remember, we didn't pay $25 for the car. We paid 25,000. So when we want to look when x equals 8, that's representing thousands. So 8 equals y. And somewhere along here, come on. Well, let's get rid of this function. I'm not sure why it's not working. Let's try this again. Y equals 8. And enter. There it is. There's our function right down here at the bottom. So we want to estimate when that is going to be. So if we touch those two graphs, at year 7.001, the car will be worth 8,000 instead of 25,000. So let's go back to the problem. I'm actually, before I do that, going to come here and use my snipping tool. And I want to grab a snippet of this. And when I go back into my notes, I can actually paste that snippet. Let me extend the page here. And I can paste that graph. And let's make it just a tad smaller. And so when y equals 8, x equals 7.011. So in 7.0011 years, the car will be worth $8,000. Okay, slide 9. In 2000, the world population was about 6.09 billion. During each of the 13 years, the world population increased by about 1.18% each year. Write an exponential growth model. So they're telling us it's growth, which is good. We need to know that this is growth.